All right, so now moving on to part B. We've got another inequality question, but of a different kind. It's given that A and B are real numbers, P and Q are imaginary numbers. And then what you're asked to do is to determine with reasoning, and I want to emphasize that right now, you can't just substitute some numbers in and see what happens. We want to try and identify what are the appropriate inequality signs to fit in here to make these statements always be true. So how do we do this? I want you to have a look at these expressions that you can see here. There's either going to be a less than or greater than, less than or equal to, greater than or equal to, right? How are we going to get some sort of sense out of this, being that it seems like we know so very little about the values of A, B, P, and Q? Well, we want to think about, for example, if P is a purely imaginary number, then P squared has to be negative. Right? That's what it means to be purely imaginary. If you square that, you're going to get a negative number. Over here, same deal. Q squared is Q is purely imaginary, so Q has to be purely negative. Now, what does that mean? Well, it's going to tell me that I've got two negative numbers over here. How does that relate to over here? Well, I need to do a bit of careful algebra to see what's going on. So now that you're getting a sense of how I'm going to solve this, let me show you my working. Since A is real and P is purely imaginary, that makes AP purely imaginary. So you can see me thinking about this thing here, A squared, P squared, as the square of AP, right? And I can make the same argument about BQ, it's purely imaginary. But if you've got AP and BQ independently being purely imaginary, then when you take the difference, they will also be purely imaginary, or they'll be equal to 0 if the two things are equal to each other. Now, if you've got AP minus BQ being purely imaginary or 0, then when you square it, you're going to get something less than 0. Or equal to 0. So I'm getting this statement here, and then when I expand it, you can see I'm getting something like the result I needed. I've got my A squared P squared on the left hand side with the B squared Q squared. There's the 2AB PQ, which I got by adding this to both sides, and you can see the direction of the inequality. It's all good. I've got a less than or equal to. Then when I have a look at the next one, have a look at the different combination of numbers. If P and Q are purely imaginary, then when you multiply them, then the i's will cancel with each other and they just leave you with a real component. And of course, we already know that A and B are real, so its product, A times B, must be also real. So AB minus PQ, unlike AP minus BQ, AB minus PQ, man, it's so easy to get it wrong. That has to be a real number because it's the difference between two different real numbers. So real numbers, we know when you square them, they are greater than or equal to 0, unlike the imaginary ones up here, which are lesser than or equal. So once I expand that out, same deal happens. I add 2AB PQ to both sides, and I've got an inequality going in the opposite direction. So that's how I identify this is greater than or equal to, this is less than or equal to, and very importantly, to get those full marks, we need to see the reasoning. You couldn't just like state it, you had to show me why. All right, let's move on to the next question. Over the page. A very, very succinct question, but a ton of work that comes out of it. So what is being asked of us? Prove Delmarva's theorem by mathematical induction, and then, please note, non-negative integer powers. Now, I'm highlighting this because Delmarva's theorem, as we remember when we first proved it, it's actually true for all integer powers. And that's really one of the most handy things about it. But in this case, what we want to prove is for non-negative integer powers. And the reason I'm doing that is actually to do you a favor. In order to prove something by mathematical induction that covers both numbers to negative infinity and numbers to positive infinity, because mathematical induction is a one-directional process. You start at a base case and then you just keep on going, k plus 1, k plus 1, k plus 1, right? In order to do all integer values, you have to start somewhere and then do your proof by induction, and then using some other mathematical tools, you have to deal with the other side. Mathematical induction ignored all of that because it just went plus 1, plus 1, plus 1. It never goes minus 1, okay? So me telling you, just do it for the non-negative integer powers is actually giving you a bit of a helping hand. You only have to do half of the proof. The only catch is, a lot of you read non-negative and you thought that it meant positive. There is a single number that is neither negative nor positive. That's 0. So therefore, the first problem that people had was, instead of testing correctly n equals 0, which was the correct base case, that you needed to verify, a lot of people tested n equals 1. And as we saw earlier in this paper, and you've seen throughout extension 1, n equals 1 is the normal place where it starts, but this was a trap for young players. We actually had to start at n equals 0. So here is Delmarva's theorem. I've stated it and you ought to know it well enough by now. So I'm going to test out the left-hand side for n equals 0. You test out the right-hand side. It's all good. We assume our statement is true for n equals k, and then we set to work trying to prove the result true for n equals k plus 1. Now you can read this yourself. This is kind of the classic proof. I've even done a whole video lesson about it. Importantly, what I've done is I've sort of expanded out here, but not like completely. I've just taken this cos theta plus I sine theta to the k and separated out because that is what my assumption includes. I've then done the substitution of the assumption, and then I've just basically expanded out. Now I will make one note, which is that some students went straight from this line here to this line here, which is semi-legitimate because what you're doing when you're multiplying complex numbers, here's cos theta plus I sine theta multiplied by this other complex number, cos k theta plus I sine k theta. When you multiply complex numbers, we know that what you do is you add the arguments. And so you can see here, one of the arguments is theta, one is k theta, off you go. What I will caution though is that if you did that, you really needed to say something like, multiplication of complex numbers results in the addition of arguments. This is a proof after all. There's absolutely an obligation on you to be able to show the reasoning for every single line that you write. In this particular working, you can see on the page, I have avoided the necessity for that by just sort of going the long way round. I've just crunched out the algebra, I've just expanded these guys out, and then I've collected like terms. And then from here, I've used trigonometric identities. So just as an example, oopsie daisy, I'm zooming in. You can see that this matches, this is like a sine A cos B plus cos A sine B situation. And what that's equal to is this part here, sine of A plus B. So that's a fairly classic extension 1 result. Doesn't have to make any argument about multiplication of complex numbers and addition of arguments. But either way is fine, I will admit. This is a fairly long and obtuse way to write it. But once you get there, you get to say, well, that's equal to, I factor out the theta, and that's the k plus 1 step. So I'm finished. Most people had no trouble with the induction. The most common error was this base case up here. So please, please, please read carefully. Okay, and now the last one in question 6. It says, consider the sequence 7, 11, 15, 19, 23. Seems like a reasonable enough sequence, will never contain a square number. What a fascinating result. What's going on here, right? Hopefully, I made it obvious enough by the terms that I included, 7, 11, 15, etc. This is an arithmetic progression or an arithmetic sequence. I'm not adding anything up, right? I start at 7 and then I just add 4 every single time, okay? How do I prove that this sequence will never contain a square number? Well, we did this quite badly as a question because a lot of people looked at this and modeled around algebraically but didn't really know what to do. This word never, I'm highlighting it because it's the big clue. When you see the word never, it's kind of a signal to you that the tool in your toolbox for the nature of proof that you need to use is a proof by contradiction. What you want to show is that you can assume that it does happen somewhere, eventually a square number appears, and what you can prove is that that's ridiculous. It leads to something absurd. There's a self-contradictory thing. That means, well, I thought it might contain a square number, but I've shown something ridiculous result. So therefore, my assumption must have been wrong. It can't possibly ever contain a square number. So if you didn't realize you could do this by proof by contradiction, you were in some trouble from the outset. Let's have a look at how you actually do it. What I've done is proof by contradiction begins with the negation, right? So you have to say if this particular sequence, it's a 4n plus 3 sequence where n starts out at n equals 1, so that's why you get 7 to begin with and 11 and so on. If I assume the negation, what that means is there exists some value of k such that in this sequence, and every term in this sequence is in this form, 4n plus 3, there should be a k squared in there somewhere, right? It should appear. So this is my negation, and what I want to show is that this assumption is clearly going to lead to some problems. So the negation is false. That means the original statement is true. So what I've then decided is, let's try it out by exhaustion, which is to say by cases. First, I've thought about what happens if k is even. Let's see what happens. If k is an even number, like 2 times something, then it's going to be 4p squared, because it's 2p times 2p. But 4p squared is a multiple of 4, right? That's an integer, p squared, and then you multiply it by 4. So this has to be some kind of whole number multiple of 4. That means it can't possibly be 4n plus 3, because 4n plus 3 will never be a multiple of 4. It's always one short of a multiple of 4. And you can see that in the examples here, right? Short of 8, short of 12, short of 16, short of 20, and so on, right? So I've proved that k can't possibly be even. Now let's see what happens if it's odd. If you try out k being odd, let's let it be 2p plus 1 instead of 2p. You do the expansion, there's k squared, and then you can see I can factor out 4 again from these initial terms. So it's going to be 4 times an integer plus 1. Well, that can't possibly be 4n plus 3, because 4 times an integer plus 1 is 1 more than a multiple of 4, but this is 3 more than a multiple of 4. You can see if I go back to my question, 1 more than a multiple of 4 would be something like 5, and then 9, and then 13, and then what's my next one? 17, and so on. And you're always going to miss. You're always going to be 2 off, because this sequence is 4n plus 3, and what I've found is apparently a 4n plus 1, if k is odd. Well, what I've just determined is k can't be even, k can't be odd. That's a contradiction. No such k can exist, which is what I've written here. So that means that the assumption, which we began with, is false. The negation is false, which means the original statement is true. An original statement and its negation has to have opposite truth values. So if one's true, the other's false, and vice versa. So that's how you use it. It was slightly tricky that I didn't tell you it was a proof by contradiction, but part of the point here is that not just can you use the right proof tools, but you know when the right tool is appropriate for the job.